Hello, my name is Caelan Garrett, and this is our work on robotic manipulation for 3D printing. This is work done at MIT jointly with CSAIL and the MIT Architecture Department. Robots are increasingly being used in construction for assembly, welding, fabrication, and 3D printing, which is the subject of this talk. Many structures that we'd like to print are optimized to have desirable strength properties, but as a result have complex topologies. These structures can't be constructed using traditional layer-based 3D printers. Thus, we instead seek to use robot manipulators. However, planning both the high-level order in which to extrude each element as well as the low-level robot motions to do so can be quite challenging. Most existing algorithms for these problems are very specialized, require strong human guidance, and often have no theoretical guarantees. Here's an example of a real-world robot printing the Klein bottle. The robot is a KUKA arm outfitted with a custom end effector that is able to extrude plastic line segments in 3D space. Printing the Klein bottle is particularly difficult because the elements overlap quite a bit. Also, there isn't an obvious ordering of elements to a human that will enable the robot to successfully perform the full sequence of extrusions. However, using our algorithms, we were able to successfully plan to print this structure, which has around 250 elements in only 10 minutes. Throughout printing, the robot must obey geometric constraints, namely that it avoids colliding with the structure and that when printing, its end effector's tip follows the line of each element. Additionally, the order in which the robot prints each element induces a sequence of partial structures, each of which must satisfy certain structural conditions. In this work, we consider a stiffness constraint on the maximum allowable deformation of the structure's nodes due to their self-weight. We compute the deformation of each node using finite element analysis, and it's important because if the deformation exceeds the tolerance, then the elements printed in the future may fail to connect at the intended nodes. We present several probabilistically complete state space search algorithms for extrusion planning. Here, the state consists of the currently printed structure and the robot's configuration. At each state, the search selects the next element to be printed, samples the end effector orientation for the extrusion, performs constrained motion planning to find the trajectory of the robot that actually extrudes the element, and finally plans a transit motion from the robot's current configuration to the initial configuration of the extrusion trajectory. Our first algorithm is a simple forward search that adds elements to the structure, which can be seen as constructing the structure during planning. However, it frequently encounters dead ends due to collision constraints. The figure on the right visualizes the first time the forward search backtracks when printing the base of the Klein bottle. The purple elements were printed first, red elements were printed last, and black elements have yet to be printed. As we can see, the long black element in the middle of the structure can no longer be printed because the robot prematurely printed the left side of the structure. Even an improved version of forward search that performs forward checking in order to try to detect dead ends earlier still gets trapped. This motivated us to explore searching in a different manner. Namely, we wanted to follow the general principle that it's advantageous to search from the most constrained part of the problem to the least constrained part of the problem. Intuitively, this is because the planner has the fewest options during the most constrained part of the problem and thus is unable to make premature decisions that restrict what it can do in the future. Notice that the collision-free configuration space of the robot decreases after each extrusion, simply because we're adding another body to the world. Thus, the collision-free configuration space is smallest and therefore most constrained at the end of construction when all the elements have been printed. Rather than start at the initial state and build forward, we can start at the final state and move backward in a regression search. This can be seen as deconstructing the structure through removing each element. Thus, now with respect to geometry, we're starting at the most constrained state and moving towards the least constrained state, which is the initial state. However, a complication is that the stiffness constraint is most constrained at the beginning of construction. On the right is a visualization of a dead-end state of the regression search. Here, the black elements have yet to be removed. What happens here is that the algorithm prematurely removes elements that are critical for supporting the structure, causing it to no longer be stiff. Because of this, the stiffness and geometric constraints are directly at odds with each other. We then wondered if we could bias the regression search to prioritize decisions that would enable the structures to maintain their stiffness properties. One thing we could do is we can consider the elements in an order determined by a heuristic. Intuitively, we might want to prioritize removing the elements that are furthest from ground first. Here, the distance from ground can correspond to the z-coordinate of an element or even the distance from ground to the graph of the structure itself. An alternative approach is to combine forward and backward reasoning. We can perform a forward search for a sequence of elements that satisfies the stiffness constraint, ignoring the robot and thus the geometric constraints entirely. Then we can use the indices of elements in that plan as the heuristic, where elements with larger indices are removed first. This encourages the backward search to adhere to a sequence known to be successful as much as possible. We performed an experiment that involved just the stiffness constraint and found that the ordering heuristics indeed greatly improved the success rate of regression, and the stiff plan heuristic performed the best among the three heuristics. We compared our algorithms and heuristics on a benchmark of 41 extrusion instances with up to about 900 elements. This bar graph shows the success rate per algorithm and heuristic pair across our benchmarks. The regression search outperformed the forward searches, and among the heuristics, stiff plan performed the best, with Euclidean distance falling not too far behind. Finally, this scatter plot shows the runtime of each algorithm per number of elements in the structure. Not only does our regression algorithm solve around 90% of the problems, its runtime also scales almost linearly with the size of the problem. In conclusion, we presented efficient algorithms for robotic extrusion planning that are able to plan for large structures, all while satisfying the involved geometric and structural constraints. Thank you.